Hi, I'm Kylie, and I'm Juwan, and we're gonna teach you about neuron signaling.
Here is a neuron.
On the left, you can see the soma or cell body, which contains the cell's nucleus and various other organelles.
The smaller branches extending from the soma are dendrites, which receive stimuli.
The large branch that extends to the right is the axon, which transmits signals to other cells.
Surrounding the axon is the myelin sheath, a layer of electrical insulation produced by supporting cells called glia.
In the central nervous system, these glial cells are called oligodendrites, and in the peripheral nervous system, these are called Schwann cells.
Each group of glial cells makes up one myelin sheath, and the space between each sheath is called a node of Ranvier.
At the end of each axon is a synaptic terminal, which directly transmits the signal to another neuron or muscle or gland cell.
The cell transmitting the signal is called the presynaptic cell, and the cell receiving the signal is called the postsynaptic cell. So now you know a little bit about the structure of a neuron.
Oh, but how does it actually create the signal?
The answer is through an action potential.
An action potential? What's that?
Let's see. At resting state, the inside of a neuron is polarized at -70 millivolts.
Along the axon, the sodium-potassium pump is at work pumping sodium out and potassium in, which keeps the cell polarized.
At this stage, most voltage-gated ion channels are closed, and there is a higher concentration of sodium outside and potassium inside.
Let's take a look at how a pump works.
In this simplified video, the white shirts represent the sodium-potassium pump, embedded in the membrane, represented by black shirts.
The blue shirts are sodium entering the cell, and the red shirts are potassium exiting the cell.
Sodium binds to the sodium-potassium pump and stimulates phosphorylation with the addition of ATP, causing the pump to change shape and release sodium into the extracellular fluid.
Potassium from the outside of the cell then binds to the pump and is transported into the cytoplasm of the cell by another shape change. So that was an action potential.
No. That was a sodium-potassium pump. That was only active at resting state. An action potential is activated by a stimulus and occurs as a series of reactions that you are about to see.
Let's do it!
Yeah! A stimulus causes sodium channels to open. The chemical and electrical gradients cause sodium to flow into the cell through these open channels. When the cell reaches threshold, which is the potential that an excitable cell membrane must reach for an action potential to be initiated, it goes through depolarization. The threshold value is about -55 millivolts for mammalian neurons.
Let's see how this happens in a membrane. The action potential begins, and several other sodium channels open all down the membrane.
Sodium rushes in, bringing the cells close to the resting potential for sodium, which is 62 millivolts.
Because sodium channels close soon after opening and potassium channels open, the membrane does not actually reach this resting potential.
This depolarization stage is called the rising phase.
As sodium channels open, so do potassium channels.
Potassium ions move out of the cell through these channels, causing the cell to return to a polarized state.
This is called the falling phase.
At the end of this phase, the membrane potential comes close to the equilibrium potential for potassium, which is -90 millivolts.
Potassium channels close and some sodium channels open, causing the membrane to return to a resting potential.
This process occurs down the axon membrane until it reaches a synaptic terminal. So you talked about myelinated axons earlier. What does that have to do with action potential?
Here, I'll show you.
Myelination causes signals to travel faster down an axon.
The action potential can only be carried out at each node of Ranvier because the ion channels cannot open where the axon is insulated by the myelin sheath.
This causes the action potential to jump between nodes.
This action is called saltatory conduction.
Also, an axon with a greater diameter conducts action potentials faster than that with a smaller diameter.
This is due to the increased surface area, which allows more ion channels to open at once.
So that's an action potential.
Yeah! Now let's look at a neuron synapse.
This illustrates a neuron synapse.
Here's how it works.
This is the presynaptic membrane.
This is the postsynaptic membrane.
Now, we and our friends will show you the synapse.
Yes, we will.
Lay.
So, what was actually going on there?
I'll take you through it again. These green molecules are calcium entering the presynaptic cell through a voltage-gated calcium channel.
This triggers the blue synaptic vesicles to fuse with the black presynaptic membrane and release the pink neurotransmitters contained within them.
The pink neurotransmitters diffuse across the synaptic cleft, which is the space between the two cells.
They enter the postsynaptic cell through ligand-gated ion channels in its membrane. Okay, so I think I get it now. The first thing that happens is the action potential.
And what is that?
That's the progression of depolarization that occurs down the membrane and carries a signal down the axon.
Good! I'm glad you learned all that. What happens specifically?
So, the sodium and potassium ion channels open in succession and conduct the signal by going through depolarization, repolarization, and finally returning to the resting state.
Awesome! So what then happens to the signal to transmit it to other cells?
A synapse.
Go on.
The vesicles within the presynaptic cell fuse with the membrane and release the neurotransmitters which cross the synaptic cleft and enter the postsynaptic cell.
And what triggers all that?
Calcium entering the presynaptic cell.
Fantastic. So, what makes all this happen?
A stimulus?
Yep. That one stimulus causes all these reactions in your cells. And it all happens instantaneously. Too fast for you to even process.
Wow, this is all so interesting.
This complex process enables the gymnast to transform the simple stimulus into a
Front tuck step out, round off back handspring, double twist.
Thank you for watching.
I hope you learned a lot.
Yay!